ATLAS is one of the large multi-purpose experiments at the Large Hadron Collider here at CERN. We've just performed a brand new, very precise measurement of something called lepton flavour universality. And leptons are a type of fundamental particle. You'll be most familiar with an electron, which is one of the components of atoms, for instance. There are other leptons, known as muons and tau leptons, which are exactly the same as the electron, but slightly heavier. And the universality of lepton couplings is the expectation that these leptons are all equally likely to be produced by a W boson, which is the particle responsible for the weak force.
So this is a fundamental assumption of the Standard Model. There's nothing to say that it should be true or should not be true, and therefore we want to test this fundamental assumption as precisely as possible. So what we did the measurement of is the ratio of the W decaying to muons and to tau leptons, and this is predicted to happen at the same rate in the Standard Model, and we want to test as precisely as possible if this happens with exactly the same probability. So one of the reasons for carrying out this measurement is that at the previous collider at CERN, the Large Electron-Positron Collider, which operated in the 1990s, they observed a discrepancy in this very same quantity. They looked at WW events and they measured the rates of decays to taus and to muons, and they found a discrepancy to the Standard Model which the likelihood of happening just by chance was at about the 1 in 100 level, and therefore this made this a very important thing that we wanted to check whether what they were seeing was a fluctuation or whether what they were seeing was new physics. So the LHC, the Large Hadron Collider that's currently based at CERN, is a hadron collider, and therefore the events are a lot more messy than at the previous collider, and therefore it's a lot harder to do these kind of precision measurements at a hadron collider.
So for this particular measurement, what's extremely important to reach the high levels of precision that we needed was to obtain a very clean and unbiased sample of muons and tau leptons. And the way that we did this in this new approach that the ATLAS measurement uses is to take a huge sample of top anti-top quark pair collisions. About 100 million of those were produced in the LHC in the dataset that we used, and use them, and within them look for the W bosons that then decay to the muons and tau leptons.
So the way we go about doing this analysis is that muons produce a very distinctive signature in our detector. They interact at various different points, and therefore you get little single dots, and you can join the dots and form a track. Tau leptons also decay to muons very often, but they do so after flying a certain distance. And therefore we can look for muons from tau leptons and muons directly from W bosons and look at the displacement from the interaction point to see if they've flown a short distance and then been produced or been produced straight away. So our measurement is of this ratio of the probabilities of a W decaying to a tau divided by the probability of the W decaying to a muon. And you see a value very close to 1 within our uncertainties, and our uncertainty is only 1.3%, which is about half the LEP value, which is a combination of all the 4 experiments. And therefore the Standard Model survives the stringent test of lepton universality.
Measuring this kind of interaction at this level of precision at the Large Hadron Collider 10 years ago was not even really thought to be possible. Being able to perform measurements at this level of precision at the LHC is a really important proof of principle and really demonstrates that the LHC is not just a search machine looking for very high mass new particles, but it also helps us understand the fundamental particles of nature at a precision level which in itself is sensitive to looking for new physics.